Okay, let's start with the very first topic, and that is phase controlled converters. As all of you are aware, phase controlled converters are basically used to convert AC voltage to variable magnitude DC voltage. Now, the input voltage is fixed in magnitude as well as in frequency, and the output voltage is regulated or a control level output. As far as power flow is concerned, power can flow from AC to DC side, that is from the source to the load, and then it is called as a rectifier. But it is also possible that the power flows from the DC side to AC side under certain conditions, and then it works as inverter. Now there are several types of phase controlled converters. Some of the converters you must have studied in your previous course. But if you put all these converters together, you can classify in several categories. One way of classifying the converter is whether it is a single phase or a three phase. Depending upon the power level, you can have either a single phase converter or a three phase converter. There are multi-phase converters also possible, but those converters are basically derived from the standard three phase converters. Converters can be uncontrolled one or a controlled one. Uncontrolled means diodes are used as switching devices. Controlled means some or all devices are the silicon controlled rectifiers. When they are the controlled converters, they can be further classified as half controlled or fully controlled. Half controlled means the output voltage, average output voltage polarity is always positive. It could be always negative, but it will be only of one polarity. And fully controlled means output voltage can be both positive or negative average value. These converters, they use SCRs and diodes together, while this one use all SCRs. There is another way of classification, and that is whether it is a half wave or it is a full wave. Half wave converter means the output voltage is available only in one half cycle of the input supply, normally the positive half cycle. Full wave means output voltage is available in both the half cycles, positive as well as negative. And then you can have single phase uncontrolled converter, single phase controlled converter. It could be three phase half controlled converter. It could be three phase fully controlled converter. You can have single phase half wave. You can have three phase full wave. All sort of combinations are possible depending upon the requirement and the power level. There is another way of classifying, and that is on the basis of number of output pulses. How many pulses are there in one cycle? You can have a single pulse converter, you can have two pulse converter, you can have three pulse converter, you can have 6 pulse converter, 12 pulse, 24 pulse, maybe 18 pulse, maybe 36 pulse, maybe 48 pulse converter, and so on. If I say single phase half wave, it means only one pulse is there in a cycle. You can say it is a single pulse converter. If it is a single phase full wave, then there are two pulses in one cycle. We say it is a two pulse converter. Three phase half wave, there are three pulses in one cycle. That becomes a three pulse converter. Like that, you can have more and more number of pulses, and if you can recall, more the number of pulses, better is the output voltage. Let's start with the first one, and that is single phase half wave controlled converter, and see how we can analyze the operation of this converter. Why I am taking this simple one? Because whatever steps are there in the analysis of this converter, same steps are followed in rest of the converters. Single phase half wave controlled converter. Circuit can be drawn like this. Since there is a single phase supply, so single phase supply is used. Half wave means only in one half cycle the output voltage is available, and since it is a controlled one, so that device is a thyristor. So this becomes a single phase half wave controlled converter, and then one can connect a load between these two output terminals. You have the input voltage, and across the load you have the output voltage. This is your thyristor, anode, and the cathode. Now how we can analyze this particular circuit? To analyze this circuit, first we have to see whether the thyristor is forward biased or reverse biased, and so on. Although the circuit is very simple, one can directly say in the positive half cycle of input voltage the thyristor is forward biased. But if you have more number of devices in a circuit, then the best way to find out whether a device is forward biased or reverse biased is to follow a procedure. And for that, what we can do, we can replace this thyristor by a switch which is open. And now we can see the voltage of anode with respect to some reference point. That reference point can be anything, but let's take this as a reference point. We can find out the voltage of cathode with respect to the same reference point. And once we have the voltage of these 2 points with respect to this reference point, we can find out the voltage of anode with respect to cathode. Remember, you should always draw the anode voltage with respect to cathode, and the advantage is that directly from the voltage polarity you can say whether the thyristor is forward biased or reverse biased. Let's say the input voltage is a sinusoidal voltage √2V sine of omega t. and let us say the load is resistive. We can draw the waveforms. Since it is replaced by a switch and the switch is open, so voltage of anode with respect to this point is basically the input voltage. And the voltage of cathode with respect to this point depends on the load. Since the load is resistive, circuit is open and therefore the current is zero, and therefore the drop across resistance is zero. Output, the voltage of cathode is basically zero. And the difference of this voltage and this voltage is basically this vertical distance, and this if it is positive, thyristor is forward bias, if it is negative, it is reverse bias. So this is how we can determine the biasing of the thyristor in any circuit. Now once the thyristor is forward bias, we can trigger it at a particular instant, or in converters we say we can trigger it at a firing angle alpha by giving a short duration pulse. Now how to define this angle alpha? Normally students say it is the instant when you are triggering the thyristors, but in that case it should be called firing instant, not firing angle. If it is a firing angle, then it should be measured from a reference point. Now question is, what is the reference point? Here it appears to be the zero crossing point. But if I have a circuit like this, where we have a DC source also, then anode voltage is like this, cathode voltage will be like this, and the thyristor will become forward bias from this point onwards. Do we measure firing angle from this point? No, because this point depends on the magnitude of this voltage, and if it is changing, this intersection point keeps on changing and the reference point will keep on changing. Reference point should be independent of the output voltage or the nature of the load. The definition is like this. Note down. Firing angle is the angle by which the conduction of thyristor is delayed, and it is measured from the instant, and it is measured from an instant when thyristor becomes just forward bias with resistive load. So with resistive load, thyristor becomes just forward bias at this point, and that's why firing angle is measured from here. So at this particular angle alpha, this switch is closed. Now when this switch is closed, input voltage appears across the load, assuming ideal device. So the output voltage becomes this, and before this the output voltage was 0, the switch was open. How long the conduction will continue? For that you have to see the current. If you see the current, this is a resistive load, and therefore the voltage output divided by resistance, that is the current. Voltage output is same as the input voltage, and therefore it is given by root 2v by r sine of omega t. We can draw the current waveform. From 0 to alpha, the current is 0 because the switch is open. And from alpha onwards, the current depends on the output voltage, voltage divided by the resistance. So at an angle pi, the current becomes 0. When current becomes 0, the device is switched off, commutated. Current cannot flow in the reverse direction, and therefore the current becomes 0. It means till pi the output voltage follows the input voltage, and after that output becomes 0. If you look at the current waveform at this point in a zoomed way, the current is like this. It goes negative and then suddenly it drops to like this. Because what happens when input voltage becomes negative, the carriers starts flowing in the reverse direction, current becomes negative. But when the majority carriers flow in the reverse direction, the outer junction layer, the J1 and J3, it's a 4-layer device, J1, J2, J3. The outer junctions, they become reverse bias, and therefore depletion region starts developing across J1 and J3. And the moment two depletion layers are formed, the current is interrupted, so the current becomes 0, and then only the reverse leakage current flows through the circuit. From the analysis point of view, we can say current becomes 0 and that's all. From the design point of view, you will have to consider these small currents, reverse leakage current and so on. Now as far as the voltage across the device is concerned, that can also be drawn. If you look at this circuit, your input voltage is equal to the device voltage plus the output voltage, and therefore the device voltage is input voltage minus the output voltage. From 0 to alpha, input voltage is this much, output is 0, so the difference is from alpha to pi, output and inputs are same, difference is 0, ideal device. And again from pi to 2 pi, input is this, output is 0, difference is . You can see that from 0 to alpha, the thyristor is in the forward bias mode. It is triggered by giving a short duration pulse. Thyristor goes into forward conduction mode. It continues to conduct till the current becomes 0, and then the reverse voltage appears across the device. It is in the reverse blocking mode. This is how you can draw the output voltage, output current and the voltage across the device. Once you have drawn the waveform, you can also find out the average voltage and the average output current. Average output voltage, fundamentally it is 1 upon 2 pi 0 to 2 pi instantaneous output voltage d omega t. It is a periodic waveform. From same cycle to cycle, same thing will happen, and therefore we can find out the average output voltage by finding the area under this output voltage curve and divided by time period, that is total 2 pi. So it is 1 upon 2 pi. Only from alpha to pi output voltage is same as input. Rest of the time it is 0. So if you simplify this, it is root 2v upon 2 pi minus cos omega t, and if you put the limits, it will become 1 plus cos of alpha. So by changing the firing angle alpha, you can find out the average output voltage. What about the current? As far as current is concerned, one can find out the average current in the same manner. Area under the current curve divided by the total time. So it is 1 upon 2 pi 0 to 2 pi instantaneous output current 1 upon 2 pi. Only from alpha to pi current is there, and that current is root 2v by r sine of omega t d omega t. If you simplify this, what you will get? Root 2v upon 2 pi r, again minus cos omega t, limits alpha to pi 1 plus cos of alpha. If you look at this portion, root 2v upon 2 pi 1 plus cos alpha, that is equal to v naught. So you can say it is v naught by r. So average output current is coming out to be average output voltage divided by resistance. It is not true under all conditions. Remember this point. It is coming out to be true in this case.